ladies and gentlemen, I feel, oops, I'm moving this out of the way real quick. Ladies and gentlemen, I feel compelled to tell you that you are now being recorded. So if you do anything stupid, it will be recorded for posterity. Well, if you say anything stupid, if you just do something without any noise, this recording won't know about it. But so if you feel compelled to say something stupid, remember that it will be recorded and posted to the internet. So just do with that information what you will. Yeah. All right. So today we get into the next part of chapter 1, and that unit 1, and that deals with measurement. Isn't it just reading the ruler? Yes and no. So first, all right. We talked about in science, when we do science, what are we doing? We say this is science, right? What did we earlier we kind of talked about what science was, right? What is science? What are we doing here? What? Good.
The study of simple and small numbers of rules that govern the universe.
The study of simple and small number of rules that govern the universe. Why? How do we figure out those rules? Do you want help?
Can I make a guess?
Sure.
By conducting experiments?
Kind of. Kara, what were you going to say?
By finding patterns.
By finding patterns, especially patterns in... What are we looking for patterns in? Yes. How do we find these patterns in the universe? We have to do what? Finding patterns in the data. In data, where that data comes in two forms, qualitative and quantitative, right? So we say that qualitative data is what? Description. But quantitative data is numbers. There has to be a way for us to get reliable numbers and make sure that we're all kind of on the same page. So something to keep in mind. When we encounter numbers in this class, those numbers are not just numbers. They are some quantitative measurements of some aspect of the universe that we live in and study. In math class, it can just be this. In math class, going back to the question you asked me before the quiz, it can just be the square root of 49, and that's fine. But here, when we're talking about 49 in science class, 49 what? Where did that 49 come from? What are we measuring that, what 49 things are we measuring? Keep that in mind, that as we talk about numbers in this class, they aren't just numbers. There's some measurement, some quantitative data about the universe that we live in. What does that require? That requires a system to make sure that everybody measures things the same way. Because if we don't all measure things the same way, Max's measurement of 49 somethings may be different than my measurement of 49 somethings. And that's a problem, especially if we're trying to measure the same thing. Exactly. If there's 49, we're measuring piranhas, right? It's important whether to know there's 49 or 4,900, right? Granted, that's a big difference, but if we're not measuring them the same way, we could have an issue, right? All right. That being said, do we know about this system that we have used to make sure that we're all measuring the same way? We call it something, the metric system. The metric system, that's kind of a slang term for it. It has more of an official name. Anybody know what the official name is? The SI system. Right, all right. So, the SI system. The SI system is a system agreed upon by scientists to produce consistency in measurement. SI stands for two French words that are basically the equivalent of the international system. Except in French, it's like Système International. Pardon my French, if you want. So, but it's created to make sure that we're all measuring the same way. And the only way that we're going to make sure that we're measuring the same way is if all of our measuring tools are the same. So we base this measurement system on some aspect of the physical universe that is easily verified and always constant. If you go to Google Maps or Google Earth or whatever it might be, there is a measurement system on there, right? You got little compass rose, and it has the little measurement map scale and stuff like that. That map scale is always based on meters or kilometers, depending on how big or small the map that you're looking at is. The thing that makes that work is that a meter here is the same as a meter, I don't know, in Texas or in London or in Singapore or wherever we might be. Okay? But if we encounter another kind of map, right? Let's say like a treasure map, right? A pirate treasure map. Yeah, right? The distances on the pirate treasure map are based on what generally? Steps, right? 47 paces towards the tree. Turn left. Take 46 paces this way. Jump over the pond at 49 piranhas. Or 4,900 piranhas. But how come we don't measure things in steps, generally? My step is different than your step, right? So there has to be some way to make sure we're all on the same page. The only way to do that is to find things in the universe that we consider to be constant, that we consider to not change. One of those things we consider to not change is the speed at which light travels in a vacuum. All right? So we know, first of all, it's really, really fast, and we'll learn that number later on, but we consider that speed of light not to change. That being the case, if I'm measuring the speed of light here in Ohio versus somebody else measuring the speed of light in London versus somebody else measuring the speed of light on the moon, we should all get the same number. That being said, we can then base distance on that number because it's always the same. Right? So, the SI system is based on some aspect of the universe that is easily verified and always constant, or at least we believe it to be always constant. Is it possible that tomorrow we may measure the speed of light differently? The speed of light we would consider to be a fact about the universe. What do we know about facts? They can be changed as long as what? How do we change it? There's supporting counter evidence. Supporting counter evidence. Is it possible that we may measure the speed of light differently tomorrow? Yes. Is it probable? No, but it's possible. Right? All right. Okay. The measurement system that we use is based upon what we refer to as base units. Base units are the fundamental measurements that we use to describe an object. Base units are basically one-step measurements. As you can see underneath where you're writing on your outline, there are a certain number of things in the universe that we measure in one step and one step only. First, length. Length is a base unit. You can measure length in one step. Boom. Okay. Mass. Mass is a base unit. It takes one measurement to measure mass. The same thing is true of temperature, of time, of the amount of a substance that is there. Okay? Some of those you might be familiar with, others you might not. By the end of this class, you will know all of them quite well. The middle column is the unit that we measure those different things in. So the base unit for length is a meter. Now you're probably familiar with fractions of that base unit, right? Like centimeters or kilometers. Or kilometer is a multiple of that base unit, right? But the base unit, right, is the meter. We use the lowercase m to represent that meter. The base unit for mass is a kilogram. I know that's confusing. Why isn't it in gram? Just roll with it. Right? I don't have a good answer, honestly. Okay. So a gram is pretty small, but whatever. I can't, other than that's the way it is, I can't give you a good reason for why the kilogram is the base unit instead of the gram. Temperature. Temperature is measured in Kelvin. There are other scales to measure temperature in, but those are not base units. They're based off of something else. Time is measured in seconds. Obviously, there's some multiples of time, like a minute, an hour, and a year, and stuff like that. But the base unit per second, or time is second. And the amount of substance is called mole. Now, notice there's only 5 up there. There's a couple more base units, but we don't come across them in this class, so I just kind of left them off the list. But there are several aspects of the universe, things we want to measure, that we can't just do in one step. For example, speed. What do we measure speed in? In order to calculate the speed of something, what do we got to know, Carter? Distance and time, right? We can't do that in one step. We got to make 2 measurements to do that, right? We got to measure distance, and then we got to measure time. So we have base units, which are like one-stop shop measurements, but then, disregard that, we have derived units, where base units are the fundamental measurements that we use to describe an object. Derived units are a combination of 2 or more base units. Sometimes it's just 2, like with speed, distance and time, meters and seconds. Sometimes it can be more than 2. Sometimes it can be up to like 4 or 5, depending on how complex the measurement of some object or substance we want to make is. We just kind of keep putting things together to represent different things. So base units, 1-step measurements, derived units, multiple-step measurements. Now sometimes we might have an instrument that combines those 2 measurements at the same time already, like a radar gun, right? A radar gun measures speed. Really, a radar gun measures distance and time, and then it calculates speed for you automatically, right? It makes those 2 measurements and it automatically does the calculation. But in order to get a derived unit, we need to measure at least 2 things. Okay. Good there? All right. Okay, units. I hope by the time we're freshmen in high school, we understand why we have to use units on numbers, yes? Why do we have to use units on numbers? What are we talking about, right? Numbers are measurements. What exactly is it that you're measuring, right? And if we go back to our example at the beginning, right? Max 49 what, right? 49 piranhas, 49 meters, whatever it might be. You got to make sure that these numbers, because remember, the numbers that we talk about in this class are measurements, okay? Sometimes we'll come across numbers that don't require units, and we'll talk about those special cases and why they don't require units, right? But most of the numbers that we deal with this class have a unit on them. Okay. All right, ready for the magic, how it happens? Okay. Okay, how to measure. We will get a lot of practice doing measurement in this class, right? But there is a certain technique that we use to do it. Every measurement has 2 parts. The first part of our measurement we refer to as our certain digit, or our certain digits, because there may be more than 1. That's, like its name suggests, the part of the measurement that we know for sure. But every measurement that we take has an uncertain digit. The uncertain digit is our best guess as to what the actual value of that measurement is. Something that we have to get straight right now and carry it going forward. Every measurement that we take, regardless of how precise or expensive a tool that we use to measure is, has some uncertainty to it. There is no such thing as an exact measurement. It's a function of us being human and the limited tools that we have to measure with. We can get close, we can be pretty sure, but there's always going to be some degree of uncertainty because of how we measure and what we use to measure. No measurement is exact. They're only good as the tools that we use and the person using those tools. Okay? That being said, let's take a look at this ruler. okay, which shows up on the back of your paper. Okay. So this ruler is a 10 centimeter long ruler, okay, and it has each of those centimeters marked off. And then, let's say I draw this line on my 10 centimeter ruler, okay, which you guys have drawn on there already. Okay. All right, every measurement has two parts, certain digits and uncertain digits. Based on this ruler and this line, there are two things that you can tell me for sure about this red line. Two things and only two things that you can tell me for sure. Carter, what's one thing you can tell me? It is longer than 5 centimeters. That's one thing you can tell me. The other thing is, it's shorter than 6 centimeters. Those are the only two things that you can tell me for sure about that red line. Okay? That being said, based on this ruler, right, we have one certain digit. We know that this line is going to be 5 point something centimeters. It's bigger than 5, but it's less than 6. Okay? Now, the next part is required. It's uncertain, but it's required. Knowing that it's bigger than 5 and less than 6 leaves a lot of wiggle room for the length of this line, right? Especially if the ruler we're actually using is this big, right? There's a lot of wiggle room between 5 and 6. So now we have to narrow it down a little bit. The next part of your measurement involves guessing. It's an educated guess, it's an informed guess, but it's a guess. How far is it between 5 and 6? Aaron, how far is it between 5 and 6? About 2/3 of the way, which is okay, but I'm going to tell you in a second that that's not quite good enough, okay? To me, it looks maybe a little bit farther than 2/3. To me, it looks like it's about, I don't know, about 70%, right? So a little bit farther than 2/3 of the way. Pretty close, but a little bit farther, okay? So, I have to then estimate how far I think it is between the previous line that I know and the next line that I know. To me, it looks like it's about 70% of the way. So I show my uncertain digit by 1 decimal place after what I know for sure. The correct recording of this measurement by me would be 5.7 centimeters. Okay? Good there. Anybody disagree with my measurement of said line? I'll come back to this. All right. Let's move on to this ruler. Notice the change that I made in this ruler from the previous ruler. So what's the change on this ruler versus the previous ruler? Jack, is that a hand or you just kind of Adam, go ahead.
You're adding basically millimeters.
Okay, I've added millimeters, right, or tenths of centimeters, right? So now I know my centimeters a little bit more accurately. Okay? I'm going to draw this red line on my ruler. Okay? Every measurement has two parts, a certain part and an uncertain part. What do we know for sure about this red line? Dina, go ahead. So it's past 7.7, but shorter than 7.8. Those are the two things I know for sure about that line. Okay? That being the case, this measurement would have 2 certain digits. Why? Why does this measurement have 2 certain digits and the last one only had 1? That's good.
Because there are 2 numbers you need to be sure of, 7 and 0.7.
And you know, and why is that different for this measurement than the previous measurement?
Because the previous measurement we weren't sure what the decimal point was.
Because
It didn't tell us
it didn't tell us where.
on the ruler.
On the ruler. Certain digits are determined by the ruler that you're using. They may vary depending on different rulers, but the certain part of your measurement is always determined by the ruler that you're using. Okay? How many certain digits there are depends on what ruler you're using. Okay? So this one has 2 certain digits because we're using a different ruler. But, we know it's between 7.7 and 7.8, but just like the last measurement, that leaves a lot of wiggle room. Dina, to you, how far does it look like it is between 7.7 and 7.8? A fifth of the way. So what fraction might that be? Sorry, that is a fraction. Let's put it in a percentage. About 20%, okay? Decimal wise, what would that be? 0.2. Except in this case, right, because we already have a 0.7, right, it would actually be what? 0.02, right? It looks to me and Dina that that line is about 20% of the way between the 7.7 line and the 7.8 line. We have one uncertain digit, and that makes the recording of this value 7.72. Okay. Question. How many of you, if I asked you, because Dina volunteered to answer, but how many of you, honest show of hands, I'm not going to make you talk, just an honest show of hands, how many of you would have said, that looks to me like it's about a quarter of the way between 7.7 and 7.8? So I might have written, hold on, this. I might have written 7.725. Okay, I saw a couple people, right? Not uncommon, right? That's okay. But there's a problem with that measurement. Okay?
It assumes that you know that the 2 is confirmed.
Okay.
It's a
How many uncertain digits does each of our measurements have?
1.
1. The last one is the guess. Okay? And it's the only one that can be the guess. Writing this value for this measurement, Adam, implies that you know what?
The 2 is a certain digit.
That the 2 is certain. In order for you to write this measurement for this ruler, for this red line, you would need to know where 7.72 is and where 7.73 is. But does this ruler give us that information? It does not. So even though you might think it's a quarter of the way, you can't use 0.25 as your estimation because now you're estimating 2 digits. Okay? Same thing if we go back to this one. Okay? It's probably not uncommon that if I asked a good portion of you, some of you would say, oh, that's 3/4 of the way between 5 and 6. And therefore, I would write this as 5.75 centimeters. Because it's 3/4 of the way between 5 and 6. But if I write 5.75 centimeters, what am I implying there? That you know where 0.7 is, and you know where 0.8 is, and how far is the line between 0.7 and 0.8? About halfway. That ruler doesn't show you that though, so you can't do that. You can only estimate 1 digit past what you know for sure. Okay? All right. Let's take, all right. The number of certain digits can vary depending on the measurement tool. Remember, certain digits depends on what ruler we're using and the lines that are on that ruler. But one thing that doesn't vary is the number of uncertain digits. There is always only one uncertain digit. which is an estimation of how far it is between the last certain digit and the next certain digit. Or how far is it between the two lines on the ruler that you're using? How far is it between the previous one and the next one? Certain digits can vary depending on the ruler that we use. There's always only one uncertain digit though. Maddie, go ahead.
If you only have one uncertain digit,
Yes.
if it's like 3/4 the way,
Yep.
would you put it into percentage instead of?
No. It's got to be a decimal. That's how we estimate how far it is between the previous one and the next one. Okay? Remember, Maddie, it's uncertain. Okay? That doesn't mean it's wrong. Alright? If we go back to this picture, okay? To me and Dina, look at this. Okay? To me and Dina, that looked like it was about 20% of the way between 7.7 and 7.8. But you might look at it, Maddie, and go, wait a minute, that's clearly 30% of the way between 7.7 and 7.8. So you would record that as 7.73. Are you wrong? No. Remember, that last digit is uncertain. It's your estimation of how far it is between 7.7 and 7.8. So, the point being, all of our measurements don't have to match numerically. But they do have to match in the number of places that they have. Right? Remember, you can't do this. Even if you think it's a quarter of the way between 7.7 and 7.8, that's not how you record that. You got to make a choice, whether it's 20% or 30%, because you can only do one extra decimal place. Okay. Good there? All right, let's take a look at these last two here. Okay. The total number of certain digits and uncertain digits is called this number of significant digits. Next week, we will spend a couple of days. Next week, we will spend a couple of days talking about significant digits and how that affects the calculations that we do with our measurements. Because remember, measurements are uncertain. If we use uncertain numbers to calculate other things, we're not sure about the answer. Okay. All right. On your sheet, there is a third ruler. Notice there is one change that I made about that ruler from the previous two rulers. Figure out what that change is and record a measurement for the triangle labeled number 1 on your page. Record a measurement for the triangle labeled number 1 on your page. Pay attention to the lines, which ones are marked, and how many of them there are. All right, so there are only 2 lines that are actually marked on this ruler. Here's 7.1, here's 7.2. Sometimes, like on this meter stick and a lot of other rulers that you're going to use, the lines are so close together that they can't exactly label every single one. But if we count between 7.1 and 7.2, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines, right? Meaning, each one of these lines represents 0.01. Probably have more time than that. All right, hey, do something for me. The other sheet that I gave you at the beginning of class today is called Measurement and Precision Practice. I would like you to try some of this evening. The answers are posted online if you want to check. We will talk about them tomorrow morning at the beginning of class. Have a good evening, everybody.
Yes.
Raquel, you gonna be good to get to your next class?
Yeah, we will.
Okay.